This is the first in a series of videos designed to help you understand how one diagram can be used to depict many different changes in a patient's body fluid status. A volume osmolality diagram, shown here, can be used to depict changes in both volume on the x-axis and osmolality on the y-axis. The solid black lines on the diagram outline the normal expected values for an adult, and the colored boxes illustrate the patient's actual values. The yellow box on the left side of the diagram represents changes in the intracellular compartment, while the blue box on the right side of the diagram depicts changes in the extracellular fluids. The extracellular fluids consist of the plasma, interstitial fluid, and lymph. The patient boxes can move to represent changes in the volume or osmolality status. Let's look at the x-axis first. You'll notice that 15 liters is considered a normal value for a patient's extracellular volume. If the extracellular volume increased above 15 liters, we would see the blue box become wider, reaching outside of our black box. If the extracellular volume decreased, the blue box would become narrower. For the intracellular volume, please notice that the box is anchored in our diagram at the center. So in this case, during an increase in the intracellular volume, our box would become wider, stretching to the left of our normal value of 25 liters. During a decrease in intracellular volume, our box would become narrower, moving into the right of our diagram. If we then examine the y-axis, for an increase in osmolality, the boxes would become taller, stretching above the normal outline. For a decrease in osmolality, the boxes would become shorter, moving below the normal value of 300 milliosmoles per liter. In order to visualize how a volume osmolality diagram might be altered, let's picture a situation where a patient is dehydrated. I've depicted the boxes as being set on wheels, indicating that they can be moved across the diagram. During dehydration, a patient would first lose a volume of fluids from the extracellular space, so we should see our blue box become narrower. As the patient loses water, the solutes that are left behind would become more concentrated, which we can represent here as the extracellular box becoming taller. Now, if we consider the cells of the body, they would be in a hypertonic solution, with the concentration outside of the cells being greater than the concentration inside the cells. Due to this osmotic gradient, water would exit the cells via osmosis, moving towards the extracellular compartment. Note that this water movement due to osmosis causes the intracellular compartment to have an increased concentration. So an important fact to remember is that while temporary differences can occur, the osmolalities of the extracellular and intracellular compartments will eventually be the same due to the movement of water by osmosis. In this case, we illustrated the changes in volume and osmolality in a step-by-step fashion to illustrate the process. On assessment questions, you will only be asked to show the final effect of the changes, which we will practice in upcoming videos. When solving a volume osmolality case, there is a specific sequence of reasoning that you should follow. First, determine the effect of the situation on the extracellular fluid volume. Given the stated condition, would the extracellular fluid increase, decrease, or stay the same? Once you've decided the effect on extracellular volume, you should then proceed to examine any extracellular osmolality changes. If there is no change in the extracellular osmolality, then there will not be an effect on the intracellular compartment. Please remember that water will only flow by osmosis across the plasma membranes if an osmotic gradient exists. If the osmolality of the extracellular fluid does change, then you need to determine the resultant effects on the intracellular volume and osmolality. In this case, water will move by osmosis, and the osmolalities of the two compartments will equilibrate over time. So, when solving cases, on the y-axis, our two boxes should always be at the same osmolality. When thinking through this process, I find it best to return to the basic principles you learned about osmosis in general biology. Let's first look at the scenario in the center of the screen. Here we see a cell placed in an isotonic solution, meaning that the osmolality of the fluid inside the cell equals the osmolality of the fluid outside of the cell. While water can still move across the plasma membrane, relatively equal amounts of water move into versus out of the cell. So in an isotonic solution, there is no change in the intercellular volume. In a hypotonic solution, shown on the left, the osmolality of the solution is lower than that inside the cell. In this case, water would enter the cell by osmosis, and the cell would swell and could potentially burst. In a hypertonic solution, shown on the right, the osmolality of the solution is greater than the fluid inside the cell. Water would travel towards the high concentration of non-penetrating solutes outside of the cell, leading to shrinkage of the cell. It is very helpful when solving volume and osmolality cases to revisit these basic concepts to determine how changes in the extracellular osmolality may affect the intracellular compartment. Now that you have a basic understanding of volume osmolality diagrams, please feel free to view the upcoming videos that relate to clinical cases in medicine and dentistry.